Are you able to access Canvas, Jada? Are you able to find my course in Canvas? Or are you just going from the email that I sent you to get in? I want to remind everybody too, I didn't get to tell everybody on video, even though it's in the syllabus. If you guys have any problem with your name or your face appearing on the internet, because all of these videos that I make, I record, I mean, all of these classes that I hold, I record them and then I post them on my YouTube channel. So they'll be on the internet open to everybody to see. So if you, for instance, have a first and last name that you don't want on the internet, or if you don't want your face to be seen on the internet, one, you should go ahead and change your username to something a little less conspicuous. Maybe, something involving your initials and then some random letters or whatever. But the main thing is don't put your name up there if you don't want your name on the internet. And the other thing is if you don't want your face, you need to let me know both of those by mail or by text message. And then I'll go out from there and try to remove them. Uh, so make sure you guys do that if you don't want to be on the internet. I don't, some people could literally be in witness protection. I literally had a friend in witness protection with me in grad school, and that kind of thing really happens. So if you don't want your name to be seen or you don't want your face to be seen, you need to let me know. There you go. There's not a separate Canvas course for the lab. I do all my labs right through class. So the way I'm doing the lab for you guys is tomorrow at 11, I think I said 10 a.m. Tomorrow at 10 a.m. I'll go online and Zoom and give an intro to this week's lab, and then it'll be due by 11:59 p.m. on Thursday of next week. Well, let's go ahead and get started because I don't want to get any further behind in the class, of course. We're trying to knock out chapter one. And last time in chapter one, I did manage to show you a case where we're actually working what I call dimensional analysis and unit analysis, and that's a key part. So what I'd like to do is go ahead and do another example like that, so you'll have some idea again of what dimensional and unit analysis is. And not only that, I'll give you an opportunity to do an extra credit just to make sure you're up to speed on this. So I'm going to go ahead and share my screen. So I'm going to share my iPad screen. And this should pop up in a second. And what I'm going to tell you is there is a formula that we can derive, and later in chapter 14, we'll derive this expression. But specifically, there's a formula for the period of a pendulum. And it turns out the period of a pendulum for a pretty large number of angles. In other words, not just a couple degrees, but you can literally go up to on the order of 20 degrees and not have more than 1% error. But there is a formula for the period of a pendulum, and the period of a pendulum will be the time required for it to go from hanging straight down to max this way to max the other way and then hanging straight down. That's a whole period. Another explanation of the period is from all the way one way and all the way back. That's another version of the period. You could also do it from this side and say all the way from here to here and back. That's a period. And that period is a unit of time, and there's a formula for it. What we know is the period of a pendulum T. Actually, I don't want to write that in blue. I want to write that in blue, not red. The period of a pendulum, we think, is a function of the length of the pendulum, L, and it's a function of gravitational acceleration, G. Uh, Now that I've explained to you what the word period means, a period is a unit of time, and therefore it has to have units of seconds, or it has to have dimensions of t. So what that tells us is t is it when I put square brackets around it, that's the symbol that we use in physics to say, hey, I don't care about the variable, I care about its units only or its dimensions only. So if I wanted to use units, I would say it's a second, but if I wanted to use dimensions, which I do, then I would put a capital T there. You can see there's a little bit of issue with that. Specifically, we use the same symbol T for it. So what we often do when we're talking about a period is instead of use T, we actually use the Greek letter tau. So we can do tau like that, and then instead of this being a period T, it's a period tau. So I'm going to work again with dimensional analysis. What I'm telling you though is that the period of the pendulum is a function of the length of the pendulum and gravitational acceleration, and that's it. Now, what we're going to do is I'm asking you to use that information to derive a possible formula for the period of the pendulum. So, in order to do that, you need to know what the dimensions of L are and the units of L. And the dimensions of L in terms of units is just the meter, but in terms of dimensions, it's the capital L for length. And you also need to know the units or dimensions for gravitational acceleration, which is what G is, and that's meters per second. And I do recommend you calling it per second, even though you can write meter per second squared all day long. The main reason why is when you get into chapter 2 and chapter 3, a lot of people run into a problem not understanding the difference between acceleration and velocity and speed. But if you learn acceleration as meter, sorry for a second. If you learn acceleration as meters per second, that makes it a little easier to understand. Specifically, if, for instance, an object has an acceleration of 10 meters per second, and it starts off at initial velocity of zero, then if I dropped it and it was accelerating at 10 meters per second every second, what that means is at 0 seconds, since I dropped it, then its velocity would be zero. But after 1 second, its velocity would be 10 meters per second. And then after another second, it'd be 20 meters per second. And after another second, it'd be 30 meters per second. And then that helps set in your mind exactly what we mean by acceleration. Acceleration has units of meters per second each second, and it tells you basically how much the velocity or speed changes per second. So with that in mind, there's the actual units for G. I'm going to use the dimensions for G though, and the dimensions for G are L over T squared. So the way we actually derive a formula for a equation, if you will, for a specific variable is we need to know the units that the specific variable that we want to know a formula for has, and we need to know the units are the dimensions. And you guys should be able, if I give you the dimensions, you should be able to write the units. If I give you the units, you should be able to write the dimension. But either way, the main thing is you have to have the variable with its either unit or dimension, and then the variables that that variable depends on with its unit or dimension. I don't have to give you both, but I have to give you some. Okay. As the semester progresses, you'll learn things like the period of a pendulum, that the length of a pendulum is length. You'll learn that the gravitational acceleration is in meters per second, and that sort of stuff. So I wouldn't have to specify those, but right now I do. So here's how I'm going to write that. I'll say tau should be equal to some function of L times some function of G. Now, in order to make this as generic as possible, I have to multiply both the L and the G because those are the two variables that we depend on. Now, that doesn't automatically imply multiplication. It might actually be division, but the main thing is we either have to multiply the two numbers at some power or divide the two numbers with some exponent or something like that, but we really don't have any choice, and this is the most general way it could be. So what I'm going to do is I'm going to imagine the length of the pendulum is raised to the p power, and I'm going to imagine the gravitational acceleration is raised to the q power. Now, with that in mind, I can go ahead and write this in unit form or dimension form, but I'm going to do dimension form. And the left-hand side is just the period of the pendulum, which we know has dimensions of time. And since we're solving for it, we don't solve for t squared. We don't solve for t to the fourth power. We don't solve for the square root of t. We solve for t to the one power. So, or for tau to the one power. So I'm going to write the dimension of tau, which is t, raised to the one power. Now, I happen to know that on the right hand side, I'm not only going to have t as a dimension, I'm also going to have L as a dimension, but I'm not solving for that. Still, I know the right hand side is going to have L on it. So the only way I can do this is I can write L and raise it to the zero power. And that's because any number other than zero raised to the zero power is one. So t to the one power times L to the zero power is just t. So that's how I know the left hand side's right. Now, the right hand side, I've got to take the dimensions of L, which is L, and I got to raise it to the P power. So this is going to be L to the P. And now I've got to take the dimensions of G and raise it to the Q power. So in this case, it's L over T squared raised to the Q power. So now I can go a little bit further and say t to the 1 power times L to the 0 power is equal to L to the P power, L to the Q power divided by t to the 2q power. Remember, when you raise a power to a power, the powers multiply. So, like if I take 2 squared, which we know is 4, and then I try to square that, then, well, actually, I shouldn't do square because they're the same if you add them or multiply them. If I raise 2 to the 2 power and then I cube that, then that's 2 to the 2, parentheses, raised to the third power. And we know 2 to the 2 is 4. And when we raise 4 to the third power, that's 4 times 4 is 16 times 4 again is 64. And we happen to know that 64 is 2 times 2 times 2, that's 8, times 2, that's 16, times 2, that's 32, times 2, that's 6, that's 30, that's a power of 6. And of course, 2 times 3 is 6. So that's how we knew that 2 raised to the 3 power, or I should say 2 raised to the 2 power raised to the third power is 2 to the sixth. So now that I have that, I'm going to simplify this by going ahead and treating the two L's. Notice I have L to the P times L to the Q. And when you multiply two numbers with the same base, their exponents add. So that's going to give me L to the P plus Q. Now, there's only one existence of t, so I'm going to write it right here. And since that's in the denominator, we can bring it to the numerator by changing the exponent to a negative. So that's a negative 2q. Okay, so now I can see t to the 1 has to be equal to t to the negative 2q power. So from this alone, we can see that negative 2q is equal to 1, and I'm going to call that equation 1. And we can also see that P plus Q, which is the power of L, that has to be equal to 0, and I'm going to call that equation 2. So from equation 2, we get P is equal to Q. I'm going to call this 2 prime. Okay, because it's basically 2 just written in another way. So the fact that it should be a P equals negative Q. Sorry about that. So one's positive, one's negative. That's the main thing. So that's equation 2 prime. Now I can plug that in. Yes. Now I can plug that in. I think that's it, right? Negative 2Q. I can take equation 1. That only has one variable. So I can solve that for Q. And that's going to give me Q is equal to the negative 1/2 power. And I'm going to call that equation 1 prime. Okay. So now I can apply equation 1 prime to equation 2 prime, and I'll see that P is actually equal to the negative Q of Q, which is the negative of negative 1/2. So that's going to be the positive 1/2. So now I have that P is equal to 1/2 and Q is equal to -1/2. So if we go back to our original formula was tau is equal to L to the P power times G to the Q power. And we've now figured those out. They're both 1/2, but one's a -1/2 and the other one's a +1/2. And an exponent of 1/2 means the square root. An exponent of -1/2 means the square root, but in the denominator. So in this case, we're going to say tau turns out to be the square root of L over G. And lo and behold, that turns out to be exactly the right answer within a factor of 2 pi. Basically, when you do this type of thing, you can get the right formula up to any arbitrary dimensionless quantity. So it could be multiplied by a million, it could be multiplied by pi, it could be multiplied by 2 pi, it could be divided by pi over 18, all sorts of weird stuff. But any pure number you can't sense out from or suss out from a dimensional analysis. Anybody have any questions on that? Okay. So last time when we actually did this, I think that was this right here. Yes, we worked out this problem for the Planck wavelength, and I did it in dimensional analysis as opposed to unit analysis. So, what I'm going to advise you to do now is for extra credit, you can do both of these as a unit analysis instead of dimensional analysis. So, I'm going to go ahead and write that down real quick. For extra credit, and I highly recommend you do this, even though it's extra credit, just to make sure you know what we're talking about on how to do this stuff. Determine a formula for the Planck wavelength and another for the period of a pendulum using unit analysis. Now remember, unit analysis and dimension analysis are the same thing, but the difference is we'll use meters, kilograms, seconds for unit analysis, whereas we use capital M, capital L, capital T for dimensional analysis. Okay, so that's an extra credit you can do. Anybody have any questions on that?
How would, like, so with the one that you just did as an example, what
Mhm.
would we do to do the unit analysis?
Okay, so what you're going to do is you're going to say tau in unit wise is going to be equal to L unit wise times G unit wise. But to allow all the different possibilities, you might say that L is going to be raised to the P power and that G is going to be raised to the Q power. And now instead of having tau, which is a unit of time, raised to the 1 power, you're now going to say seconds to the 1 power times meters to the 0 power. So that's the units for the left hand side. The right hand side is going to be the units of meter raised to the P power. And the other one, the G, is going to be meters per second raised to the Q power like that. So now you just solve for P and Q just like I did before, only you're using lowercase m, lowercase s, lowercase t type stuff.
Oh, okay.
Does
Okay,
that
got
make
it.
sense, Michelle?
Yes. Yeah.
Okay.
Thank you.
Anybody else have any questions like that? Now, here's the notes from last time, and you can find those either by going to the video or going to my Google Docs. But that was the result we found last time. was the Planck wavelength was equal to the square root of the gravitational constant times Planck's constant divided by the cube of the speed of light. Okay, and that is the actual formula, by the way. Let's try another one just to make sure everybody's on the same page. Uh,
I'm
yes,
sorry, I
go
have a
ahead.
question really quick. The one that you just had up, I was trying to look back through my notes. I don't see it. I don't know if that was one that we didn't get to the
Oh,
other
oh, gotcha.
day.
Yeah, I
Okay.
forgot I had done this. So what I did last time was we didn't get to it in time. So I went ahead and put it at the end of the video. So if you and I even made a note on it. If you look on my YouTube channel, it says basically look to the make sure you run the video to the very end because I did some more stuff after everybody left.
Oh,
And
okay. Okay.
basically, it was all this. So you're exactly right. I completely forgot that I did that after class. So sorry about that. Actually, let's go ahead and go over it now because it seems like most people didn't look at that video yet, and that's okay because you were in class. Why would you necessarily look at the videos since you're actually here? But here's how I did it. In the case of what we call, yeah, now I feel really bad because I've been talking like this, like y'all knew it, and I was a complete bonehead for not knowing it. So let me show you what it is here. So there's a concept we use in string theory called the Planck wavelength, and it's sort of some measure of how small something could be. And if you actually calculate it, it turns out to be really, 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 really small, like 10 to the negative 40th or some god awfully small number like that. What we know is that the Planck wavelength depends on the gravitational constant that we'll learn about in chapter 6. It depends on Planck's constant, which we'll learn about in chapter 37, and it depends on the speed of light, which we could learn about in chapters 2, chapter 3, but ultimately we learn the most about it in chapter 36 when we do special relativity. So, in order for me to assign this type of problem, I have to, for starters, tell you what the unit or what the dimension is for the Planck wavelength. Now, it is a wavelength, and wavelength has the word length in it, so that should make you think that the unit should be meter, and that's what I'm writing right here. Is see how the Planck wavelength has units of meters. If I wanted to do that in dimensions, I'd say the Planck wavelength has dimensions of L. Okay. So now that we have that, I'm telling you that this Planck wavelength is a function of g, the gravitational constant of the universe. If you've ever watched Star Trek, the new version of Star Trek with Captain Picard and all that stuff. I'm drawing a blank on it. Oh my God. Anyways, the next generation. So if you actually watch that, you'll run into this character Q, who's supposed to be a god, and they're having a problem, and he's working on the Enterprise at the time, trying to be a human. And Geordi says, "Well, what are we supposed to do?" He said, "Well, just change the gravitational constant of the universe," which sounds like something like a quote unquote God could do, but not very helpful to Geordi. But Geordi ends up figuring out something. This is that constant that they're talking about there. So that's why I try to bring that up. It also depends on the speed of light. So we saw g, the gravitational constant there. Here's the speed of light. And the speed, just like your speedometer, has units of miles per hour. That's a distance divided by time. So you know that the speed of light should have units of meters per second or dimensions of length per time. And then finally, this one's the most complicated, but I have to give you this. So all this stuff I'm doing right here, that's me working out what the units and dimensions are. You don't have to do that. You would just be given this part, or just be given this part, or just be given this part, that kind of thing. Okay. So what I have to do now is say, okay, I want to find a function or an equation that could give me this quantity, which has units of or dimensions of L, and it's a function of G, which has dimensions of L cubed over mt squared. And it's also a function of c, the speed of light, which has dimensions of L over t. And it's also a function of Planck's constant, which has units of meters length squared over time. So just like I did before, I'm going to say the units of the Planck wavelength is equal to the units of the product of these three variables, and I'm going to raise the three variables to different powers. If I used P and P for two of them, that would automatically force me to assume that the G and the C had the same exponent. There's no reason to believe that. So I actually have to use three, since I have three constants. I have to use three individual exponent variables in case they're different. So for G, I use the exponent of P. For the speed of light, I use the exponent of Q. And for Planck's constant, I use the exponent of L. Now, the left-hand side is just supposed to be Planck's wavelength, and Planck's wavelength has dimensions of L, so I write L to the 1 right here. Now, the fact that G and C and H introduce the L, the T, and the M means that I have to have L and T and M on the left-hand side. But the left hand side is me solving only for the wavelength. So that's why the wavelength, which has dimensions of L, should be raised to the 1 power because that's what it means to solve for the wavelength. Then my unit will just come out in L's, or my dimension will just come out in L's. But it has to have some recognition for M, so I have to put that to the 0 power because that's 1, and it has to have some recognition of T, so I have to put that to the 0 power as well. Now all I got to do is take this value of G, which was L cubed over MT squared, L cubed over MT squared, and I have to raise it to the P power, so I get 3P, P, and 2P. Similarly, I have to take this L over T and raise it to the Q power, so I get L to the Q over T to the Q. And then finally, I have to take Planck's constant, which has dimensions of m L squared over T. I have to raise that to the L power. So I end up getting m to the L, L to the 2L divided by T to the L. Everybody follow that so far? Anybody have any questions on that? Let me put the chat up too in case anybody's typing anything. Thank you, Julian, for turning in the Canvas request. All right, so now that we have that, now it's just a matter of getting all of the L's as one factor with whatever exponent it has to be. So if I look over here, I've got a L to the 3P, I've got that being multiplied by an L to the Q, and I've got that being multiplied by L to the 2L. And of course, when you take two numbers with the same base and you multiply them, you end up adding the exponents. So I'm going to have 3P plus Q plus 2L, and you see that's exactly what I have here. Anybody have any questions on that step? Okay. Now I have a m to the p in the denominator, so that's technically like a m to the negative p. But I also have a no m in this one, but I do have a m to the l in the numerator, so that's like m to the positive l power. So instead of thinking of m to the l being multiplied by m to the p, you can sort of picture it as m to the l being divided by m to the p. And when you divide two numbers with the same base, you subtract their exponents. So you should get l minus p, and that's exactly what I have for the exponent on m. Anybody have a question about that?
You don't have to like indicate anything for like that middle one that's the LQ over TQ, like because there's no M, you don't have to indicate anything with that in the
Exactly.
okay.
Because all of these are just being multiplied and they're like variables, how you can cross one off. It's in the numerator and it's also in the denominator, that kind of stuff. So it's
Yeah.
sort of that kind of math.
Okay.
Okay. So now we've done the L and the M. All we're left to do is the T. Notice all the T's are in the bottom. So that means you're going to get a negative quantity. But it's T to the negative 2P times T to the negative q times t to the negative l. So lo and behold, I get negative 2p minus q minus l. Does that make sense? Anybody have a question on how I got that? All right. So now I can look at this equation and I see that the exponent on L has to be equal on both sides. So I've got one equation that says 3p plus q plus 2l is equal to 1. That's because of this. I've got another equation that says L minus p has to equal 0, and that's what that is. And then I have a third equation that says 0 has to be negative 2p minus q minus L. Now, if I start with that second one, the L minus P equals uh, 0, then you can immediately see that that gives me just L is equal to P. Now, that's not that helpful. It doesn't give me either one, but it tells me that they're equal, so that's kind of helpful. And in fact, that means I can replace all the Q's with, or excuse me, all the P's with L, or I can replace all the L's with P. It doesn't really matter which, but I can do one. Okay. So I can now take this equation and put it inside of this third equation, which is this guy right here, by just replacing this P with an L or just replacing that uh, P or that L with a P. Either one works. What I did here is I've got negative 2P minus Q minus L, negative 2P minus Q minus L. Uh, in place of L, I put the actual P. I think that's what I did. Did I write that correctly? Yeah. Okay. So I can substitute that in, and now instead of negative 2p minus q minus l, I've got to replace the l with p, and that's why that is there. Okay. Now, if I combine like terms, you can see that this negative 2p and this negative p gives me negative 3p. And then I could pull the negative q to the other side, and that would be negative 3p is equal to q. And that allows me to figure out that p is equal to negative q over 3. So now I've got L equals P, and I also have that P is equal to negative Q over 3. That's two facts that help me. So what I do now is I copy all this stuff from this bottom line and put it on the next page. So you can see all that's there. That's the stuff I just finished doing. There's my P equals negative Q over 3. There's my L equals P. I can now take the 3p plus q plus 2l and instead replace the l with p. So I get 3p plus q plus 2p equals 1. That allows me to combine the 3p and the 2p to give me 5p. And now I have 5p plus q is equal to 1. And that means I can solve for q by leaving the q on the left and subtracting 5p from both sides. And now I've got q equals 1 minus 5p. You can tell this sort of a little problem and answer session where you're just trying to figure out how to solve a system of three equations, three unknowns. Go ahead, Michelle. You have a question?
So I think I just got it. I was looking at the original says the 3p plus q plus 2l equals 1.
Hmm.
And when you went down, it was the 3p plus q plus 2p equals 1, and the
Hmm.
L was swapped because L equals P above that, right?
Exactly. Good
Okay.
job. That's exactly the type of stuff you guys got to do when you're reading the book example, is you got to figure out how did they get from this step to this. So you got to pay attention long enough to sort out the algebra that they're doing. And sometimes you even need to just take about a piece of paper and write it out. Luckily, there's not huge gaps between one line and the next in this textbook, but the further you go in engineering or physics or chemistry or biology, the more rigorous that gets. So you just got to get used to it. But absolutely, that's great that you're asking me these questions. Make sure you keep that up. Now that I have that, we've got all these different quantities. I've found out that Q is equal to 1 minus 5p. And now I can go ahead and replace this p with what we found, which was negative Q over 3. And then we'd have basically just an equation with nothing but Q in it. So that was the trick for me, is once I found P was negative Q over 3, and I have a P here and a Q here, then I can actually get rid of one of the variables by writing Q equals 1 minus 5P, but in place of the P, put in negative Q over 3. So when you do this, you see that the negative times the negative gives me a positive, and I've got now 1 plus 5 thirds Q is equal to Q. I can, for instance, subtract 3 over 3 Q to each side, and that's going to give me 2 thirds Q on this side and negative 1 on that side. So now I can finally solve and see that Q is negative 3 halves. Now that I have Q as negative 3 halves, I can now figure out that P would be negative 3 halves times negative 1 and divided by 3. And that, of course, gives me P is equal to positive 1 half. And since P is equal to L, that tells me that L is also 1 half. Now, remember our original function was lambda P gives me G to the P power times C to the Q power times H to the L power. So now all I got to do is work out what those are. So G was raised to the P power, and P turned out to be 1 half. So I have G under a square root, which is what I have there. The Q is the exponent on the speed of light. I'm going to leave that for right now. But the L is the exponent on H, and the L was also 1 half. So I can put the H under the square root with the G, and that'll take care of the L and the P. Now all I have to do is figure out what's going to happen to C, because the Q, the exponent of C, is negative 3 halves. The negative 1 half part means it's a square root and the C is going to be in the denominator, but the fact that it's 3 halves means the C has to be cubed down there. So that's the actual correct answer for the Planck wavelength in terms of G, H, and C. Any questions on that? Just to give you a little idea of exactly how small that number is, G is equal to 6.67 times 10 to the negative 11th. Let's not worry about the units right now. H is equal to basically Planck's constant, which is 6.626. I think that's what I remember. It's been so long since I've done it. 626 times 10 to the negative 30. I want to say 34th. And then C is about 3.0 times 10 to the 8th. So you're going to take a number that's about 10 to the negative 11th, multiply it by a number that's 10 to the negative 34. That's going to give you 10 to the negative 45. And then you're going to divide it by 10 to the 8th. That's going to give you 10 to the negative 53. And you're going to take the square root of that. So you basically get a wavelength that's on the order of 10 to the negative 26 power. So that's a really, really, really small number. All right. Anybody have any questions on that? All right. Just because of this, I should probably, since I ended up doing this in this class, I'm going to go ahead and copy all this in today's notes. Copy. Now I'm going to go over here and say paste. Okay, so now this will be in those notes. Now I'm going to go get the other page, which is actually a lot easier. Whoa, Nelly. Didn't mean to do that. Now I'm going to get the rest of this. Copy. Oop, didn't mean to do that either. Let's do paste. And this one's going to be a little bit harder. Actually, I think I can shrink it a little bit. Shrink it a little bit more. And let's try twisting it. Why is it not twisting now? Let's do this. Let's do paste it over here. Okay. So there's the rest of that problem. Sorry about not remembering exactly what Planck's constant is, but anyways, I haven't done it in a while. Anybody have any questions on those two dimensional slash unit analysis problems?
The only I'm a little bit stuck on the C with the exponent of three,
Hmm.
where that came from. Like I was trying to review it and I'm still
That's a old rule from algebra, basically.
okay.
So yeah, when you can write, for instance, 2 to the 3 halves, and that could be written as 2 to the 3 to the 1/2 power, right? Because a power raised to a power means multiply. So now you can see that if you multiply 3 times 1/2, you get 3 halves. Does that make sense?
Yes, yep.
Okay. And then the big deal is that if you take, let's say, x to the 1/2 power and multiply it by x to the 1/2 power, you're going to get x to the 1/2 plus 1/2 power, which is x to the 1 power. So you that shows you, oh, 1/2 means square root. So now you can say 2 to the 3 to the square root is what that is. Does that make sense?
Yes, yeah. Thank you.
Okay. Yeah, that's just some rusty stuff. You get a little rusty if you ain't messed with algebra in a little while.
Yeah, it's been like 10 years. So
it
that part's rough.
happens. It gets worse when you get old like me. So, all right. Now, there's another topic that we got to issue, that we've got to study. Last time, I just want to double check how many unit conversions we went over. I did do the density of water. I didn't actually express to you the importance of the extra credit that you can do with the density of water. So there is an extra credit you can do with the density of water. For instance, I did the density of water in kilograms per cubic meter, and I worked it out to units of grams per cubic centimeter. Now you can go from there and you can convince yourself exactly what a cubic centimeter is. So let me go to the page we're working right now. And what we found so far is that the density of water is equal to 1,000 kilograms per cubic meter. And last time we showed that that is also equal to 1.000 grams per cubic centimeter. So that's kind of neat because it's a really nice number for the density of water, so it's easy to not forget. Now, there's also a density of seawater, which I mentioned before, and we usually use that on average to be 1,025 kilograms per cubic meter. So obviously it'd be 1.025 in grams per cubic centimeter. And the only reason why I'm telling you that is that's part of what we're going to do with the extra credit problem. Now, the other thing I want you to do is realize that 1 liter, which is a unit of volume, is defined to be basically a cube whose dimensions are 10 centimeters by 10 centimeters by 10 centimeters, which equals 10 centimeters times 10 centimeters times 10 centimeters, which equals 1,000 cubic centimeters. Okay. Now, what we learned about the metric system is the prefix milli means 1/1000th. So that means 1 milliliter is equal to 1 liter divided by 1,000. And of course, if you divide 1 milliliter by 1,000, then that means you're also going to get 1 cubic centimeter. Does everybody see what just happened there and how I reached that conclusion? Good job, Michelle. Anybody have any questions on that? The left-hand side of this expression was 1 liter, and it's equal to the right-hand side, which is 1,000 cubic centimeters. So when I took and divided 1 liter by 1,000, I'm also dividing this by 1,000. And 1,000 divided by 1,000 gives me 1. So now we've discovered something new. 1 milliliter is exactly equal to 1 cubic centimeter, which you might have heard called cc. Okay. So those of you who may have had a child by now or may have been involved with a sibling when they were growing up as a infant and toddler, that's one of the first times you are confronted with this. Like inevitably, you'll go to a doctor, your child will be a little sick, they'll write a prescription for your child, and they'll give you like 5 mLs per every 4 hours. And then you go to the pharmacist, you get that prescription filled, and the pharmacist will tell you give them 5 cc's every 4 hours or whatever. And you're immediately thinking, wait a second, that's not the same thing that my doctor told me. But now you see it is. A cc is the same thing as a cubic centimeter, is the same thing as a milliliter. So that also means that the density of water can now be written as the density of water is equal to 1,000 kilograms per cubic meter. It's also 1.000 grams per cubic centimeter, but it's also 1.000 grams per milliliter. Okay. And you can go a little further if you realize that this is a little bit more complicated, but 1 cubic meter, 1 meter cubed, is equal to 1 meter cubed times 1 meter is equal to 100 centimeters. So if I cube that, I get 1 cubic meter is equal to 1 million cubic centimeters. But 1,000 cubic centimeters is equal to 1 liter. So you can combine these two to realize that 1 cubic meter is equal to 1,000 liters. So now we've got that the density of water is also 1.000 kilograms per liter. Any questions on that? I'll also mention to you, you've probably seen this riding around town. I often see landscapers and pressure washers, people that, get paid to pressure wash houses. You'll see them riding around either with a truck or a truck with a trailer, and it'll have something that almost looks like a chain link fence around a big white plastic cubic barrel, cubic bucket, if you will. And the thing is roughly 3 feet wide by 3 feet thick by 3 feet tall. In fact, it's almost essentially exactly that. It's pretty much a cubic meter of water. And this reminds you exactly how heavy water is, because if it really is a cubic meter of water, it weighs 1,000 kilograms. Does anybody recall how you convert kilograms to pounds? Perhaps someone that works in the medical field would know this, or is a biologist. Anyone? So if you take the number of kilograms that someone weighs and you multiply it by 2.2, that's a good approximation. That gives you the pounds. So what we see is 1,000 kilograms times approximately 1 kilogram is equal to 2.2 pounds. You get 2,200 pounds. Does anybody know what a ton is in our British system of units?
Is it like 2,000 pounds?
Exactly. So 1 ton is also called 1 short ton, and it's equal to 2,000 pounds. So now you know that big box that you see in the back of people's trucks or on their trailers, that thing when it's full, it literally weighs a ton. So you can't just willy-nilly go throwing those in the back of your truck and driving off, or put them in the trunk and driving off with water in it, because it's going to weigh so much it could literally cause problems, like it could kill you in a car wreck for starters, but not only that, it could also mess up your vehicle because your vehicle might not be made to carry 1 ton in its load. But not only that, you see that this one is equal to a metric ton, which is also called 1 ton because the British people spell it crazy, but it's also called a long ton. I think I've only, excuse me, I didn't mean to make that a division symbol there. I was just trying to write it under it. So it's also called a long ton. But I've literally only known one person to ever say that. So I don't know if I just heard a moron say something that doesn't mean anything, or if it really is that. And I shouldn't say moron, it's just, one person could make one mistake. That doesn't make them a moron. Anybody have any questions on that part? All right. So now for the extra credit part. Extra credit, you can see it's actually typed up in the module one. It'll actually tell you exactly what to do. But roughly what I'm asking you to do is tell me the density of water. And you can also do for seawater. I want that in, one thing you can use is pounds per gallon. And I'm just going to write a bunch of things. The actual online extra credit assignment tells you exactly what I'm wanting, but I'm going to give you some ideas of what we could do. A pound per gallon is 1 unit. We could also do kilograms per gallon. That's another one. Another one we can do, and this one's kind of weird. You can do PSI per foot. You can also do pounds per cubic foot. Okay. And you can also do other things like atmospheres per foot. Because here's the thing, the PSI is pounds per square inch. So what we're doing is we're taking the kilograms and we're going to convert that to pounds. And then we're taking the volume, which might be in cubic meters, and we're going to take two of those meters and convert them to inches, and then convert the last meter to feet, and we'll get PSI per foot. It turns out that this is a figure that you use if you actually take a scuba diving class, and you'll probably run into it if you ever do. Specifically, you get 62.4 and 64.0 for those values. But that's sort of a hint of where to go. There's also one more that I really like, and that's the ounce per ounce. That's another density unit you could use. You might not have noticed this, but that's part of the reason I'm showing it to you because people haven't always paid attention to units. But you notice if you actually like look at a box of cereal, it'll give you a serving size in ounces, but it'll also give it to you in grams, which tells you that ounces has some relationship between ounces and grams. And you might think, well, okay, are they using the density of the cereal? And no, they're not. There is a fluid ounce that's a unit of volume. So this one has to be a fluid ounce. And this one has to be a mass ounce. And actually, it's not even a mass ounce, it's more of a weight ounce. Because what it's based on is 1 pound is 16 ounces. Right? You guys know that because a quarter pounder, for instance, is a 4 ounce burger. A typical ribeye, for instance, might be 10 ounces or 8 ounces, or if you're like me, you like a good 24 ounce ribeye or a good 24 ounce prime rib. Those are all in increments of pounds. So it turns out when you actually calculate the density of water in ounces per ounce, it comes really, really close to one again. So it's just a happy coincidence that I love. So anyways, that's one of the extra credit problems you guys can solve. Anybody have any questions on that?
With the extra credit problems, like this might be explained once the course is open again, but is it like the assignment, like do we have homework and then we're submitting the extra credit through that, or is it like a separate upload?
Let me show you on our course right now. I'm going to share my screen with you.
Okay. Thank you.
No problem. That's actually exactly the kind of stuff I want to do. Okay, if you look down here, extra credit density of water, this is an actual assignment. You can tell by that little book right there. And if you click on it, it tells you, given that the density of water is 1 gram per cubic centimeter, determine the density in pounds per cubic foot. Pounds per cubic foot is another way of writing it. I'm just trying to show you guys that the pound symbol is something that we do use for pounds. It's also pounds per square inch per foot, pounds per inch cubed, and pounds per gallon, and ounces per fluid ounce. And what happens here is with this, you'll actually be able to turn it in. I've got to change the date so you can actually turn it in, but I'll say clear and I'll say the due date is a week from today, and that should work. Why is
Credit
this?
for the class itself or for lab? Is it?
It's in the course for the class
Oh,
241
okay, I see.
N02B. Yep. So I'm trying to do that. Due date.
It looks like it's saying like I wonder if maybe something got swapped.
Ah, now I know what's going on. I saw this the other day and I was like, how could this be?
Oh yeah. It looks like it's like an old course or something.
Yeah, that's crazy. This is supposed to go to May, and it's actually supposed to go to May 4th. May the 4th be with you. I'm going to book it up to there, and we'll say that that might be the reason you guys aren't seeing it, but I never typed that in. I don't know. I don't know why it was there. That's weird, but that
Have
explains what was
access
just
again.
happening.
So yeah, that's like it fixed it because I can see it now.
All right, so it was me then, and I don't even know how that came in here because I've never messed with such a thing. I just had the idea of it when I saw that it wouldn't take my change of grade or my change of due date. So let me go back down here and go ahead and change this due date properly. This should fix it. So I'm going to say edit, and I'm going to say now here, let's say save, and now it's working. Okay, so that's where it'll be turned in, and you can see how it's printed out here. You can also see the other assignment that I gave you guys. I didn't actually tell you about it. I told my face-to-face class, but the unit mass that we use, the kilogram unit mass that we use, that is actually a cylinder of platinum iridium. And to make it the least fallible that you could, they decided to design it so that it had a minimum of surface area, because the more surface area it has, the more subject to oxidation it is. And when the surface actually oxidizes, that means the oxygen's bonding to the actual metal and making it change its mass. So, in order to avoid that, they tried to design a cylinder that is has a minimum surface area. Now, you know from calculus, there's a way you can find minima and maxima. Anybody want to recall exactly what that method is to find the minima or maxima?
Second derivative.
The first derivative set it equal to zero, and the second derivative is the part that allows you to determine whether it's a maxima or a minima. So I explained that here. You can see, but basically the formula is the surface area of a sphere of a cylinder is 2 pi r squared, because the top is pi r squared and the bottom is pi r squared, and then it's the distance around times the height. The distance around is 2 pi r, so the surface area is 2 pi r squared for top and bottom plus 2 pi r h. Now that has two variables in it. It has R and it has H in it, and you guys have only technically had Calc 1, so you're not supposed to know how to do multivariable calculus. So what you can do is, you know that the density, since it's a fixed substance, platinum iridium, that density is a constant, and you also know that it's the standard kilogram, so that mass is a constant. That means the volume has to be a constant, because density is equal to mass over volume. Well, the volume is pi r squared h. So you can use volume equals pi r squared h to represent V as a function of R, or excuse me, H as a function of R, or you can write R as a function of H. Either way, you're eliminating one of the two variables in the surface area, the R or the H, and then you can take the derivative of the surface area with respect to that variable, set it equal to zero, and get an expression that relates R or H, whichever one you kept, related to V. Once you've done that, you're not quite finished. You have to then plug in the expression for V so that you can get a relationship between R and H. And that will be ultimately the formula that I'm looking for. And then to confirm that it is indeed a minima, remember y equals 2x, or excuse me, y equals x squared is a parabola that opens up. And if you take the derivative of y equals x squared, you get 2x. If you take the second derivative of y equals x squared, you just get 2, which is positive. So that shows you a minima would have a positive second derivative. So if it really is a minima, you can then calculate the second derivative with that relationship between R and H and show that that is positive. If it was negative, it would show you that it's a maxima. If it was zero, it'd show you it's a point of inflection. So that's what this example is about. Anybody have any questions on that? Okay, so that was another problem. Now, I'm going to leave the Fermi calculations up to you, that section of the book, but you can also look them up on my YouTube channel. But I am going to go over one problem. So, just to give you an idea of how to go about doing this, what I would tell you to do is make sure you can do the problem where they want you to estimate the volume of the lake. So that's a good problem. There's a problem where they're going to get you to estimate the height of a building. That's a good problem. And then there's another one where you're going to use a ladder to estimate the radius of the Earth. So what you do is find a big body of water, like the Chesapeake Bay, for instance. And if you look at the Chesapeake Bay and you see land across the water from you, you'll notice that you can't see where the waves are trickling up against the shore. It's almost like the water has bulged up in between you and the other shore, so you can't see it. But if you climb up a ladder high enough, you'll get where you can then see the edge of the water meeting the ground. Once you figure out how high you have to go there, you can use that height to solve for the radius of the Earth. And your book does that as an example. So make sure you can learn how to do that one. But additionally, that's another extra credit. If you actually take the time to find a body of water that's on the order of 6 to 20 kilometers across, then you can actually use that to calculate the radius of the Earth yourself, all on your own. So that's another extra credit. But the main thing I wanted to show you is when I took this course for the first time, it was one of the first courses I took at the university level. And I came in for my first test. That happened to be the first class that I had a test in at university after I left a community college, College of the Almars, where I had went. And Professor Adler had given us this test, and I thought his teaching was really awesome. And I came in, and he asked this question, and I got really excited. He said, "How many fruit flies can fit in this room?" And he was talking about the classroom, like the classroom that I'm sitting in, right? And that was our test question. And that's a wonderful type of question. So I wanted to explain to you how I go about doing that. So when you go to calculate something like that, you look in a room and you say, "Holy crap, I don't know how big anything is." Well, that's part of what you're supposed to be learning in this physics course is you should understand how big is a meter. You know, the meter, the unit of measurement. So how big is a meter? Well, a meter is about 39 and an eighth inches roughly. So you can see it's a little bit bigger than 3 feet. It's also, in terms of everyday life, it's about the height of a doorknob. So that's what a meter is. You also need to know what a centimeter is. Well, I'll tell you, a centimeter is about as wide as my index fingernail. Okay, so that width is about a centimeter. It also happens to be about as wide as a staple, which I happen to not have right here, so I'm not going to do that. But a staple, the actual shape that goes like this, and this, that width is around a centimeter. Okay. Now, additionally, the thickness of that metal that the staple is made of is about a millimeter. Remember, a millimeter is a tenth of a centimeter, so that helps you as well. But those are things that we expect you to know. So when you look at a classroom that you might be in, for instance, to take a test, it's very reasonable for me to expect that you can estimate roughly how wide the classroom is in meters, how long the classroom is in meters, and how tall the classroom is in meters. But if you can't, don't worry. I've got a really nice correction to that. And let me share my screen for this. So I learned this from Larry Weinstein over at ODU. He's written a book called Guesstimation, and then he wrote a second edition called Guesstimation 2.0. And it's a really good book. It teaches you how specifically to do these Fermi calculations that your book's talking about. And what he taught us was if you don't really know what a dimension is, there's an easy way around it. Like if you look at this classroom and you're like, I can't tell if that's 5 meters or 7 meters. For one, you're getting confused because you're trying to get it way too precise. These are order of magnitude calculations. So your answers are 1 meter, 10 meters, 100 meters, 1,000 meters, 10,000 meters, and that's it. Okay. So what you do is you take one measurement that's obviously too small. It's close, but it's obviously too small. So when I look at a classroom and it looks, maybe 30 some feet wide, I say, is it a meter? And I'm like, no, it's not a meter. So that's obviously too small. Then I say, well, I'm looking at the wall. Is it 10 meters? And I say, that might be right, but I'm not really sure. So I'll back off for that. Well, let's try the next one. The next one's 100 meters. And you say, well, it's definitely smaller than that. So when you've reached that conclusion, what you can do is say an actual estimate of the length is equal to the geometric mean. Now, most people don't know what the geometric mean is. In fact, I didn't know till after I got out of college, to be honest with you. But the geometric mean is we're going to take the number that's barely too small and multiply it by the number that's barely too big. Okay. And then take the square root of that. So I told you the classroom was bigger than 1 meter. So that's the barely too small. I said it might be around 10 meters. I'm not going to use that. I know it's less than 100 meters. So I'm going to use that as barely too big. And lo and behold, I get 1 meter times 100 meters. The square root of that is 10 meters. Okay. So that's the way we can estimate it. Now, the other wall I think is probably right around 10 meters. So I'm going to say the width is going to be 10 meters as well. And then I look and the ceiling looks like it's like 9, 10 feet tall. I think that's 3 meters. But again, if I didn't really have a good estimate, I'd say, is it 1 meter? Is it 10 meters? Is it 100 meters? And you'd come up with probably, you'd say, well, it's clearly bigger than 1 meter, but it's also clearly smaller than 10 meters. So for the height, I would go the square root of 1 meter times 10 meters. And here's the other thing that Larry Weinstein taught me. The square root of 10 is approximately equal to pi. So I'm going to call that pi meters. And we're not going to really say pi. We're just going to say that's 3 meters. Okay. So the volume of the classroom is equal to 10 meters times 10 meters times 3 meters, which equals 300 cubic meters. Now, my fruit fly, I'm going to guess that this fruit fly sort of is about like a rectangular solid just because I can make that easy. Now, I suspect the height of the fruit fly, it's clearly bigger than a millimeter because a fruit fly is just a house fly, by the way. Okay, the flies that you see that pester you outside or near your dinner or whatever, that's big enough. So 1 millimeter is way too small. 10 millimeters is probably too big because that's a whole centimeter, but it might be about right. So I'm going to assume the height is 1 centimeter. I'm also going to assume the width is no, I'm going to say it's probably more like a half a centimeter because it's not quite, a fly's not really that big. It's not as big as my fingernail. It's normally a little bit smaller than that. So I'm going to say zero point 0.5 centimeters, and I'm going to say it's zero point 0.5 centimeters wide, but I suspect the length is 1 centimeter. So the volume of the fly is zero point 0.5 times zero point 0.5 times 1, and that gives me, of course, 0.25 centimeters cubed, which is approximately zero point 0.3 cubic centimeters. Now all I have to do is convert cubic centimeters to meters and then divide the volume of the room by the volume of the fly. And what we find is the number of flies we could fit in the classroom is approximately 300 square meters, or excuse me, cubic meters divided by, now the cubic centimeter turns out to be, we already did that a second ago. The cubic centimeter turned out to be 1 millionth of a cubic meter. So I'm going to say divided by 0.3 times 1 million, so that's 10 to the 6, 10 to the negative 6 cubic meters, like that. And what we can see now is that we're going to get roughly 10 to the ninth flies. And that's the answer. Okay. Now, it would be a multiple choice, or if I give it to you in just a straight calculation, you just give me a number. And what's more important to me when I'm grading that type of test is looking at your approximations you made and your calculations you made. But if it was multiple choice, I'd probably have 10 to the ninth as an answer. I'd have 10 to the 11th as an answer, and I'd have 10 to the 7th as an answer. And you would obviously choose 10 to the ninth. If you got 10 to the 7th, I can say objectively you were just wrong. If you got 10 to the 11th, I can say objectively you were just wrong. You were thinking of like a beetle as opposed to an actual housefly. Anybody have any questions on that? All right. Well, we're actually finished. You guys are always free to go immediately because remember, this is sort of somewhat optional because I always record it. But make sure you chat me your first and last name if you haven't already done so. Hopefully, I've got the problem with the canvas not showing because it looks like I had that date wrong. I don't even know how that date got changed, but it was. So, uh, you guys have a great weekend. Send me an email or a text message if you have any questions or you need help or anything. I usually respond, like I said, to the emails within one business day. But if it's something urgent, then I normally can reply to a text message within usually the same day. And if I'm there and available at the time that it comes through, I usually immediately answer it. So thanks for coming, everybody. We will start into chapter 2 next time, but I will take questions on chapter 1 still as well. Thanks, Michelle. Don't forget, everybody, let me know if you don't want your face or name to show up on my interwebs on my YouTube channel. That's my legal requirement. I just don't want to upset anybody or mess anybody up, so make sure y'all do that.
Oh, Prof, I think someone mentioned that they also saw some about like a 2025 due date on an assignment or something like that. I don't know if that was mentioned already.
Yeah, so there you're
Okay.
talking about a due date of 2025 instead of
Yeah.
2026. Yeah, so when I copy my course from the previous semester, it just throws them in there with all the old due dates. So slowly but surely, I have to go through. And anytime you see one that was due 2025, you can just ignore it. It's my problem. It's my fault. So if
Okay.
you ended up not getting it done, that's my fault, not your fault. Once I change the date and make it appropriate, then it could be your fault. And basically, the way it works is roughly every Sunday you're supposed to have a homework set due or two homework sets due. And
Okay.
this particular first chapter one, I've actually made due on the 21st just to give you a little extra time. But from here on out, it'll usually be Sundays. Every now and then, I might make one part due on Wednesday and the other part due on Sunday, but that's it.
Okay, thank you so much.
No problem. Have a good one, Isaiah. Now I got to go check all my dates on the other ones, see if any other students are having problems with courses not showing up.
Thank you. Have a great evening.
You too, Michelle. Have a good day. Wyatt, Riley, Jada, anybody have any questions? Brian? Ronnie, Johnny, Mickey, and Mike?
Is real quick.
Yes, sir.
Uh, did you receive my email about the textbook?
I did see an email from you, but I was so busy I haven't been had a chance to look at it or even read it. I just know that one came, and I remember seeing your name as Riley.
Yeah, I was just because the IBM name didn't match the syllabus book, so I just sent a screenshot,
Oh,
was
gotcha.
just seeing if like that was a correct one.
I'm
But
looking for that now, and I don't see. Did you send it yesterday, maybe?
I sent it on Monday evening.
Oh, okay. So I've been a little bit back. I should have caught that. I don't know how I didn't, but anyways, let me look at it. If it's there you go.
So it should be the correct author, but it's also Pearson like 24 month.
Yeah, okay, the 24 month is what you normally want. You want at least 12 months, but 24 months is good as well. Is it fifth edition?
Dude, I would have to go back and check,
The only
but
Riley that popped up wasn't you because it didn't have an email associated with it. Did you send it to my TCC email or did you send it to a text message or?
it was through it was through the actual TCC emails, so it should be like RPK241, but it does look
Okay.
like it's a fifth edition, 22nd.
Okay, so fifth edition's the main thing, and it
Yeah.
should say with modern physics. Uh, if it
Yes.
doesn't have that, they're probably not going to let you log in.
Yes, with modern physics.
Okay, then yeah, it should work.
Okay.
Yep.
Um,
Oh, there's your
real
last name. Gotcha.
real quick, I saw part of the syllabus was face-to-face exams.
hmm
Are we going in person for that, or is that just proctored over Zoom?
you can find a proctor locally if you're not nearby. There is a way, like my plans this semester is I will have a time period during which I can proctor students via Zoom, but you'd have a lot of things that you'd have to do. Like you need to have a 8 inch by 8 inch mirror available. You need to have a phone that has a video camera and can run uh, Zoom, and then you also need to be able to run your computer on the same Wi-Fi while you're taking the test. If you can get those three things, then I can usually do it, but I usually do exactly one time in that 7 day span when you have a test due. And if
Mhm.
you can make that, that's great. If not, you have to find someone else. Like local schools will do it, local universities will do it. There are services that you can pay for online, or you can come to any TCC campus and they're all free.
Okay.
Okay.
Um, so I'll be honest, I had quite a bit of trouble following through the course today. I understood that it was a lot of dimensional analysis,
Right.
and I'm assuming like that's hopping into chapter one. Because I didn't have access to the Canvas shell, I didn't know exactly where we are. But would you
Gotcha.
just
Yeah.
recommend like going through all of chapter one, doing practice problems, building up from there?
I'd say the you can sort of get away without necessarily reading the text, the actual paragraphs and stuff like that. I don't recommend it. I recommend you trying to learn how to read the text, but as a
Mhm.
bare minimum, you have to read the examples and then follow them and work through them, sort of like Michelle was asking me all these questions. You want to do the same thing. Like you won't have me there to ask the questions, but you've got to sort of sort through the example and say, why did he do this? Or how did this, this equation work out to this equation. But if you do the examples in chapter one, you should at that time be in a really good place where you can start doing the homeworks pretty straightforwardly. If you run into problems, what you want to do then is like look for the first two or three odd problems at the end of the chapter in each subsection and try doing that. And the reason why I say the odd ones is the odd ones have the answers in the back of the book. So you can work a problem like the problem you're doing by finding one in the at the end of the chapter, working it, and then checking your answer. If you got the right answer, then you can pat yourself on the back and say, I think I've learned how to do this, and then you can attack the homework problem or you can go and do another one to make sure, or so on and so forth. So that's usually the best way. It just turns out to be initially when you're studying physics, it's all about here's a bunch of symbols that represent quantities, and here's a bunch of equation that relates those symbols.
Mhm.
Your job initially is just finding out the equation that has the things you want and the thing that you have and plugging it in. And then as time goes on, you get a little better at understanding how that's supposed to work. So there'll be a difference of you have to put a negative in sometimes, sometimes you have to put a positive, sometimes you have to add a quantity. So it's just learning that by doing the examples.
Okay. And I
It,
believe I saw there's a allowed equation sheet as well on the test.
it's allowed in the sense that I have a equation sheet that's approved, and that's the one you're allowed to do. So if you look in
Mhm.
the helpful documents and links, you'll see the equation. That's the equation sheet you're allowed to use.
Okay, I see it.
Okay.
And I also see a bunch of like the chapter practice. and all of that.
Exactly. So the way that works is the chapter practices are sort of something I don't even get to find too much about. I can tell when you're taking them, but I can't tell what grades you got or anything like that. But the way you're supposed to work is if you run into difficulties when you're taking the practice test to prepare for an online test or a face-to-face test, sometimes you'll be taking a test and you'll see, oh man, I keep getting these one types of problems wrong. And you look at it and you're like, oh, these are all chapter four problems. And the test that you're at, the practice test that you're actually taking might cover chapters one, two, three, four, five, and six. And just doing the practice test isn't going to help you with just chapter four. At that time, you go to the chapter practice and start working the chapter four ones because they're really, really short. They're literally like normally, I think I have maybe two concept questions and two problems that you work from that chapter. And you can just
Hmm.
keep skipping through them until you find the problems that you like or that you're looking to try to do and just do them repeatedly. The big thing with the practice test is the practice test is made of the same bank that I use to make the actual test. And I guarantee my students that uh, 80% of the points on any one test only come from those banks. So, in principle, if you memorized and took the practice test an infinite number of times and you memorized all the answers, you couldn't get any lower than an 80.
Okay, so you can repeat the practice test to keep practicing, getting familiar.
Yeah, and every time you do, it'll be a different set of problems.
Okay. And then like the other 20%, would you say like it's more of like you make it, you conceptualize it, or would it be like something
Yeah,
in the course, like textbook?
in principle, I would make it, but to be honest with you, in the last 8 years, I think I've actually, if I go to the last 20 years, I think I've maybe made two questions total. So, so it's always been 100%.
I mean, it's a pain making questions. You have to make sure a bunch of variables work out and all of that.
Yeah, and you got
I
to
can't
solve it and
imagine
make
for
sure
physics.
you didn't miss anything. So yeah, it's a little bit of a problem. I make up one every now and then. I make them all the time for homeworks and class problems and stuff. But making them for a test, I just haven't needed to because the students are taxed enough from the ones I give them.
Fair enough.
All
And
right.
did you say we were doing something for lab tomorrow?
Yeah, and that's completely optional, your attendance is, but I'm planning on coming in, signing on at 10 a.m. and doing the actual intro to the lab, telling you how to do it. And then if anybody has any questions, they can ask them. And that would be lecture questions or lab questions. And then you're just free to go. But normally what I do is I just put the video up and I put it on my YouTube channel, and then you guys have until 11:59 a week from tomorrow to get it done.
Okay.
Okay.
And it would be the same Zoom password meeting code.
Actually, no, I'm going to send that out. I haven't made that one yet because I hadn't decided until literally about 5 minutes before class started tonight. I hadn't decided when I was going to do it, so I'll be sending that out tomorrow morning.
I gotcha.
Okay, and yeah, that's another office hour for anybody that might want to show up, but they'd have to show up, maybe 30 minutes after 10. So like 10:30, if they show up, they can ask me other questions.
Okay. Oh, so it won't be too long. It'll just really be that introduction.
Yeah, the introduction usually takes me at most 30 minutes. Occasionally, I can run a whole hour and a half, but I rarely do that.
I gotcha.
Okay. And like I said, if you run into any problems between now and Monday, which is the next time we meet, or tomorrow and Monday, feel free to send me an email, or if you want it quicker, send me a text message. I usually don't get offended by people sending me text messages. That's why I give my numbers to people.
Well, here's the hoping Verizon comes back up.
Yeah, for real.
That time, oh my goodness.
I couldn't watch any of the news while I was driving down the road.
Oh yeah. I was sitting at
Which,
home. Fiance was at work in court, and usually I respond quickly. So, after 6 hours of not responding, she came home and was like, "What's your problem?"
yeah, exactly. What have you been doing? I didn't realize it till I got home that it was actually Verizon that was out. I was just thinking the internet was out or something, but then I got home and realized it was Verizon. So,
I finally
anyways,
didn't pay my bill.
yeah, exactly. Well, have a good one, Riley, and let me know if there's anything I can do to help you. And if don't get discouraged, like I said, I tell my students this every semester. If it starts seeming really hard and you're thinking about maybe I should drop, talk to me first. I can help you. There's a lot of ways I can help my students to get a little bit more proficient with math. I can get them a little bit more proficient with reading the book, and I can show them how to do really well. Students make a lot of good grades in my physics, my calculus-based physics class. They don't make all A's, but I normally have a good, 4 or 5 out of 24 make A's. So.
I got you. I think I need to first of all hit that book. I'll definitely finish that before the weekend, just to catch up and all of that. But
Yeah, and like I said, if you get daunted by the reading, I tell my students this all the time. What you might want to try to do is like either take your textbook or some book that you consider the most boring book in the world, okay, and start your stopwatch and start reading. And when you find your brain starting to wander, stop the stopwatch. Believe it or not, that might be a minute, that might be 2 minutes, it might be 10 minutes, it might be an hour. I'm not sure, but I've literally had people that it's been, and it would have been me as well, would have been on the order of 2 minutes when I was in high school. So that's fine. What you want to do then is the next 5 to 10 times, you only want to read for that long. And then the next time you meet, meaning you read for that long, you take a break, go do some other stuff, come back, read some more for that long, take a break, go do some other stuff. And then after you've done that 5 to 10 times, either increase the amount of time by 10% or 1 minute, whichever's the bigger, and then keep doing that for another 5 to 10 times, and then increase it again, 5 to 10 times, increase it again. And ideally, what you'd like to do by the time you graduate college is you'd like to be able to read for 4 hours straight without any problems. But a bare minimum at the TCC level, I'd say, is read an hour. So if you do that, you'll learn to be a better reader, and you actually learn to be a slower reader in some cases. That's what happened to me. But you can learn how to read slow when you're reading science textbooks and read fast when you're reading literature, unless it's complicated literature. But I definitely
mhm.
recommend doing that. It's a skill. It's one of the reasons that employers often want college educated people, even though they technically don't need college education. They just want someone that can read like a white paper that a corporation puts out, and then they can implement the ideas in that white paper. If you can't read a physics textbook, then you're probably going to have some difficulties reading some of those white papers, even though the white papers are usually easier.
Yeah, I'm hoping organic chemistry last semester conditioned me to be able to read through
That
anything.
is one of the toughest courses. So yeah, that would give you a heads up against everybody else. Not necessarily in the subject matter, just in your maturity of grading or reading and studying.
So much,
Yep.
so much fun. Well, I appreciate it, Professor.
No problem. Have a good one, Riley. Let me know if I can do anything to help you.
Awesome. Thank you. Have a good night.
You too. See you, bud.